Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abudiwa Sos Ogobela Mets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 8. It says a cleaned pure copper strip, Cu in solid form, is placed in a beaker containing a colorless silver nitrate solution, AgNO3, at 25 degrees Celsius, as shown below. After a while, it is observed that the solution in the beaker becomes blue. Then 8.1, write down one other observable change besides the solution turning blue. Right. So, okay, we know that this one, we simply just have to look at our 4B table here. And then as we can see, the comparison is between copper and zinc, right? So the one that we always locate for copper is the one that goes as 0.34, right? And then we also have silver here at positive 0.80, right? Now, looking at this, we know that when we are dealing with a galvanic cell, the one that is above is always the anode, which is the one that undergoes what? Oxidation, right? So what you always need to remember here is a red cat and ox, right? Red cat and ox. So this means that reduction takes place in the cathode, and in the anode, that's where we have oxidation, right? So this one here would be the one that undergoes oxidation, and this one here would be the one that's on the cathode, which undergoes what? Reduction, right? So observe that. Now, in this case, that means what would we say about our observation? Now, the observation would be that, obviously, considering that the copper strip is in the anode and then it's undergoing oxidation. So we'd say the copper strip, so our answer would be that the copper strip will oxidize. So that's definitely one of the observations that we'll see there. And then also number 2, the fact that our silver here is the cathode, and then that's where reduction takes place. It means now that the copper will become plated. Copper will be plated with silver, right? Remember, the silver ions are the ones that will undergo reduction, and therefore they will be the ones that will electroplate the copper, right? So copper will be plated with silver. Right. So these are the observations that we can state them, that the copper strip will be oxidized and also the copper will be plated with silver. Right. Okay, so that is it right there. So this is for 8.1.1. Okay, then 8.1.2 says the name or formula of the oxidizing agent. Note this, guys, the oxidizing agent is the one that undergoes what? Reduction. Always remember that the oxidizing agent undergoes reduction. This is the substance that undergoes reduction, right? If you want to observe the oxidizing agent, right, that means you have to check here. If you can see here, they've wrote increasing oxidizing ability, right? Increasing oxidizing ability. So on the left-hand side, that's where we have the oxidizing agent. And then at this point here, we can see that we are being told that from above to below, that's where we have an increase in the oxidizing ability. That means the more we go down the 4B table, that's where we have stronger oxidizing agents, right? So obviously the oxidizing agent always has to be observed on the cathode, because that's where reduction takes place. But then the oxidizing agent is always the one on this side here, right? So your oxidizing agent will be observed from this side. So your oxidizing agent is not the silver, but then it is the silver ion. It is very important for you to note that. So whenever you are stating the oxidizing agent, you have to look on the left-hand side, and whenever you are giving the reducing agent, you have to take the one on the right-hand side from the 4B table. So that means what is our oxidizing agent? So for the oxidizing agent in 8.1.2, we are going to say the oxidizing agent is what? is the silver ion, right? Remember, they said you can write the name or the formula. So it's the silver ion, or if you prefer to write the formula, it is just Ag plus, right? Okay, so just like that, you have your 2 marks there. Then in 8.2, they are now saying, explain the answer to question 8.1.1 by referring to the relative strengths of the oxidizing agents or the reducing agents, right? So, okay, this is how you're going to put it, right? So this is just a matter of telling us here. Remember, they said you can either explain it in terms of the relative strengths of the oxidizing agent or the reducing agents. Okay, since we have talked about the oxidizing agents already, we might just as well go with the oxidizing agents. Now, how do we explain this? This is how we're going to go about it. We're going to say, okay, observing from here, again, we can see that this is our, okay. So observing from here, we can see that this is our Cu, copper here, 0.34, and then this is Ag, right? So this is 0.80 here. Now, obviously, considering the fact that we are looking at the oxidizing agents, we can see that Ag plus here, we can say that Ag plus is a stronger oxidizing agent than what? Oxidizing agent than Cu2 plus. Remember, when I speak about oxidizing agents, I must only compare these ones on the left here, right? So Ag plus is a stronger oxidizing agent than Cu2 plus, which means that the Ag plus here, which means that the Ag plus will, remember, what does an oxidizing agent do? Ag plus will reduce to what? To Ag. That's if you choose to explain using oxidizing agents. But then again, you can explain using reducing agents, right? You can also explain using reducing agents. Remember, with reducing agents, it increases from the bottom all the way to the top, right? So that means in this case, you'd have to say copper is a stronger reducing agent than Ag, right? So copper is a stronger reducing agent than Ag, right? So copper is a stronger reducing agent than silver. So which means now what will happen? What does a reducing agent do? So Cu will oxidize to Cu2 plus, right? So that's basically how you explain that. So that's basically how you explain that, right? So basically for that 3 marks, they just give you 2 marks for mentioning this. Ag plus is a stronger reducing agent than Cu2 plus. So the fact that you have compared your oxidizing agent, that's 2 marks. And then your statement here saying that the Ag plus would have to reduce since it is an oxidizing agent to Ag, that's that mark. If in here Cu is a stronger reducing agent than Ag, that's 2 marks. And then Cu will oxidize because it's a reducing agent to Cu2 plus. That's another mark, right? So whether you explain it based on the oxidizing agent or the reducing agent, you would get your full 3 marks, right? Okay, then let's go. So pretty nice question there. Pretty nice question. So, okay, now we move to this one here. It says a galvanic cell is now set up using Cu and Ag strips as electrodes. A simplified diagram of the cell is shown below. Then 8.3 says, write down the name or formula of electrode A, right? So we have 8.3.1. What is electrode A? So as we can see here, we have the Ag plus ions. So most definitely we know that the A here has to be a silver electrode. So we're going to have what? Ag. Name or formula of solution B. Note this, solution B, the electrolyte in here. So since we have copper, we know that the electrolyte that mostly forms there is what? Is copper sulfate, right? So they said name or formula. So if you want to give the name, that's copper 2 sulfate, right? So copper 2 sulfate. Okay. And then for 8.3.3, they now say overall net balanced equation for the cell reaction. Note this, the net cell reaction. Now, the net cell reaction is not the cell notation. So always know the difference between a cell reaction and a cell notation. A cell reaction is whereby you have to first give off the oxidation half reaction, then the reduction half reaction, and then you cancel off the electrons, right? After they're balanced. So, okay, now this is how we're going to go about it. Obviously, we need our 4B table for that. So going back to the 4B table, again, remember that we are on copper. So the copper that we always go with is the one on 0.34. So do not choose any other one. So 0.34 is the standard one. And then we have this one here, right? So remember that this is the anode, right? And then on the anode, we have oxidation. An oxidation half reaction is always written from the right going to the left, right? So always when you write it, so you apply this, what we call the Z method here. So the Z method is you do like this. So always remember the arrows. If we want to write the oxidation, it's from this point going that. And then if we want to write reduction, it's from the left to the right. So, okay, now if we have to write our oxide half, this is how we go about it. Our oxide half will be Cu, and then to give us what? To give us Cu2 plus 2E, right? And then our reduction half, we're just going to write this one as it is. Note that I'm not using the double arrows here, right? Because this indicates reversible reaction. It means that this can be both oxidation and reduction depending on where you start writing it. So if we want to write it from this side to that side, then it's oxidation. If we want to write it from this side going that side, then it's reduction, right? So oxidation if it's going that side, reduction if it's going that side, right? So now that's why you must just indicate this one arrow here to show that this is only oxidation. Then reduction, also you indicate that one arrow there, Ag plus E to give us what? Ag. But then now looking at your oxidation half and your reduction half, we can see that the number of electrons are not balanced. Remember, the net cell reaction needs to be balanced. And how do you balance it? By making sure that the number of electrons are balanced out so that you can be able to cancel them. So what is it that you do now? Since you can see there's a 2 here, what you will do is you will cross multiply, right? So if there's a 2 here, you multiply by the 2 down here. Here there's 1 electron, so you want to multiply by 1 up there, right? So that's like cross multiplying there. And then obviously if you multiply everything by 1 here, it still remains the same. But then if you start multiplying by 2 here, then you have 2Ag plus 2E minus, and then you have plus, to give off 2Ag like that. So, okay, so now we can see the effect of having to multiply by that. But then now what have we achieved? We have achieved this, the fact that now our electrons can now cancel out because now they are balanced. So note that the E here is on the on the reactant side, and the E there is on the product side, meaning that they can easily cancel out now. Right? So what do we do? Cancel out this, cancel out that. And then now to write the net cell is simply we want to do this. Now to write the net cell reaction, we simply just going to drop down everything that is on the left. So that's your Cu plus 2Ag plus, and then to yield, drop everything that's on the right, that's Cu2 plus, and then plus 2Ag. Right. And then just like that, we now have our net cell reaction. Okay. So that's how you go about it, guys. That's how you go about it. So also that for 3 marks, right? Okay. Then now there's not much of a penalty if you don't write the phases, right? So some of you maybe might ask, what about the phases? In a net cell reaction, they really don't mark the phases. But then it's very important to show the phases if you are writing the cell notation. But then here, even if you don't write the notations, you will still get full marks, right? Okay, so that's your 8.3.3, guys. Then let's see, what question do we have now? Okay, then the salt bridge contains potassium nitrate, right? So they say the salt bridge contains the silver, the potassium nitrate, and then write down the formula of the ion in the salt bridge that will move into the silver ion solution. Choose from K plus or NO3 minus. Give a reason for the answer, right? Ion solution. So it definitely has to be K plus, the potassium ion, right? And then we're going to say the concentration of the Ag plus actually decreases, right? And then that means silver half cell becomes negative and therefore will attract a positive ion, right? A positive ion. So the concentration of the Ag plus actually decreases if we're going to be putting that ion in the salt bridge. And then that means now it will attract the positive ion. Okay, so this is all that will take place there. So for 8.4, you have your 2 marks like that. And then let's move to the next question. Okay, so we have yet another question 8. It says, the table below shows 2 half cells A and B used to assemble an electrochemical cell under standard conditions. So 8.1 says, state the energy conversion that takes place in this cell, right? Now we know that if we have half cell A and half cell B, we are dealing with a galvanic cell, right? So what is the energy conversion that takes place in a galvanic cell? So for our 8.1, we're simply just going to say, this is what? Chemical energy, chemical to electrical energy. There we go. So chemical to electrical energy. Then, okay, in 8.2 now they're saying, calculate the mass of silver nitrate AgNO3 used to prepare 150 centimeter cube of the electrolyte solution in half cell B, right? So calculate the mass. Now remember that this is being operated under standard conditions. And then we know that under standard conditions, the concentration of the electrolytes, right? So this is an electrolyte here. The concentration of the electrolyte is always 1 mole per dm cube. So this is the standard. Now we have 150 centimeter cube, which is obviously not given in the desired SI unit. So what must we do? We must take the 150 here, divide it by 1,000, and then we obviously going to get 0.15 cubic decimeters. Now to calculate the mass, we can pull up the formula. C is equals to mass over molar mass times volume, right? Now what is our concentration? Our concentration is 1, and then M is the mass that we are looking for. The molar mass is AgNO3, right? So if we can just quickly calculate the molar mass of this one, Ag, it gives us, what is it, 108. And then N is 14, and then plus 3 times what? Oxygen is 16. So if we calculate all of that, we are going to get what? So that's supposed to be, let's see, molar mass. So that's 170 grams, right? Okay, so we're going to have 170 here and then multiply it by 0.15. So obviously 1 over 1, if we cross multiply here, our mass is going to be the 170 times 0.15, which is supposed to be 25.50 grams, rounded off to 2 decimal places, right? So that becomes the mass, and then that's 4 marks just like that. So that's how you were supposed to calculate it. And all you had to remember is that on your standard conditions, the concentration of the electrolyte is 1 mole per dm cube. Right. Then 8.3 says, define the term reducing agent. So we've been saying it. A reducing agent is a substance that is oxidized, right? The substance that is being oxidized, right, is the reducing agent. Note, reducing agent undergoes oxidation, oxidizing agent undergoes reduction. Okay, now in 8.4, they're saying, write down the name or formula of the reducing agent. Remember, how are we going to crack that? We are going to actually figure it out from our 4B table. So we have copper here and Ag. So now we want to figure out which one is our reducing agent. But then reducing agent is the one that undergoes what? Oxidation. So that means it's going to be found on the what? On the anode. Note that. So reducing agent undergoes oxidation, it's going to be found on the anode. So that's the thought process that you should go through whenever you are answering these questions, especially when it comes to reducing agent, oxidizing agent. Always remind yourself, what is a reducing agent? Okay, undergoes oxidation. Where do I find oxidation? On the anode. Then it's easier to spot it like that. Then, so remember, we are comparing between the copper. And then we did mention now that when we have copper, we should always go for the one that goes 0.34, right? Unless from the question you can see that it has been given otherwise. But then most of the time, the one that we usually are given is this one. Then the Ag, where is the Ag? Okay, 0.80. Right. So obviously from here, we can see that this is the anode, right? This is where oxidation takes place, right? Reducing agent. So reducing agent, almost lost it there. Reducing agent is the one that undergoes oxidation, and it's found on the anode. So the reducing agent, the reducing abilities are here. So that means it has to be the copper. So copper, or you just go Cu. Did they say name or formula? Let's check. Name or formula, yes. So copper. Balanced equation for the reaction that takes place. So we already know now, going back there on our table, this is what we're going to have. So this here, being the first one to appear, is the anode. And then applying our Z method, we know that it must be written to that direction, and this must be written to this direction, right? So we have our oxidation half. Oxide half should be Cu to give us, quoted the wrong one. 0.34. There we go. Yeah. And then Cu to give us what? Cu2 plus 2E. And then our reduction half, exactly as it is Ag plus E to give us what? Ag. To give us Ag. Then again, you know what should happen? Here we multiply by 1. Here we multiply by 1. But then on this one, we multiply by 2. Right, so if we multiply by 1 here, this remains the same. But if we want to multiply by 2 here, that's 2Ag, 2E minus, and 2Ag plus. So now, these ones can now cancel out. And then we drop the ones on the left. So for net cell, it's Cu plus 2Ag plus to give us what? Cu2 plus 2Ag. And then that's what we have there. That's the net cell reaction. Nice. Awesome. Okay, then what else do we have? It says calculate the initial EMF of this cell. Calculate the initial EMF of this cell. So we're just going to go for 8.5. So this was 8.4.2. 8.5 E cell is equals to E cathode minus E anode. The cathode is the silver. And then what is the silver? The silver is 0.80, as we can see here. So 0.80. And then the anode is the copper, which is always the 0.34 there. So minus 0.34. And then 0.80 minus 0.34, that's 0.46 volts. Do not forget the SI unit. Hallelujah. Okay, so we are fine with that one. And then what else? 8.6, how will the EMF of the cell be affected if the concentration of the copper ions in half cell A increases? Note that your copper ions are on the anode. And what did we say according to this? E cell is inversely proportional to the E anode. So if you're going to be increasing the concentration on the anode, then it negatively affects the E cell. So that means our answer here is what? For 8.6, it has to be decreases. Decreases. Right. So 16 marks in the bag, just like that. Easy peasy. Let's see another question. So we have another question 8. It says an electrochemical cell is set up under standard conditions. Now 8.1 says write down one function of part labeled X. So again, our 8.1 is the Sol bridge, and then we can just go with it completes the circuit. Completes the circuit. Right, so you have seen other reasons as well. So you can write any of those. Which electrode of the cell is the anode? Write down only copper or Ag. Right. At this point, we know that our anode is the copper because we've been doing this circuit here. So it's the one that will be found above with a 0.34, and then this one is positive 0.80. So this positive 0.34, that positive 0.80. So the one that will be above is this one. Above is the anode. Then 8.3, write down the name or formula of the electrolyte in the copper half cell. The name or the formula. So you can go, in the copper half cell, we have copper sulfate, or the name is copper 2 sulfate, right? And then for 8.3.2, they say the silver half cell. So usually we have the AgNO3, or we can say it's the silver nitrate. So those are the electrolytes that we have there. Now in 8.4, it says write down the balanced net overall equation for the above cell. So it's been the same one throughout. Oxide half cell, oxide half reaction. Now we know it's Cu to give us Cu2 plus 2E. And then the reduction half reaction, then it's the one that gives us Ag plus E to give us what? Ag. Then again, you do that thing of cross multiplying. So you multiply by 2 here, you multiply by 1. If you multiply everything here by 2, then it goes like that. And then obviously this and that now cancels out, right? So now we have what? Cu plus 2Ag plus to give us what? Cu2 plus 2Ag. And this becomes your what? Your net cell reaction. Okay, so just like that, you have your 3 marks, right? Then once again, they say calculate the EMF of the cell. So let's quickly run through that. So EMF of the cell, you just say E cell is equals to E cathode minus E anode. So the reason why I did those two questions and then they almost look similar with everything, is that I'm just trying to make you see that all these questions are structured the same way. You will always be responding to one and the same questions here. So I just want you to see the structure of those questions, right? So that you get to understand the idea that when we say all of these questions are not new, they're just being adapted from previous papers, you can now understand that, right? Because those two questions were definitely from different years, but then all that was tested is the same. So it's like they just adapted this question from that question. So 8.6, state the standard conditions under which this cell operates. Its concentration of 1 mole per dm cube for the electrolyte. There's a concentration of 1 mole per dm cube for the electrolyte, and then there is a temperature of 25 degrees Celsius. Now, do not mention pressure. Do not mention pressure because, as we can see here, there are no gases, right? There are no gases. So keep it at concentration and temperature. You only mention pressure if there is a gas. So the gases that you usually see is either your chlorine gas or your hydrogen gas. But if you don't see those two gases there, do not mention the standard condition of pressure, right? So make note of that. Okay, then that's how you were supposed to go about that. 13 marks in the bag, just like that. So had you practiced that question and then this was on the year that you wrote, then it was pretty easy for you to answer that. Okay, so now let's go to another question. Okay, so we have another question 8 here. It says the galvanic cell represented in the diagram below consists of a barium electrode dipped into a barium nitrate solution and a copper electrode dipped into copper nitrate solution. Assume that the cell operates under standard conditions. Then 8.2 says state 2 standard conditions under which the cell operates. Again, we can see the very same question here. The standard conditions. So we're going to mention what? Concentration of 1 mole per dm cube, right? And then temperature of 25 degrees Celsius. Again, we are not mentioning pressure because there are no gases. 8.2, which half cell A or B is the cathode? Write only A or B. Now, obviously here, we should be looking at this based on the what? On the electron flow. So we are given this E minus here and then the arrow here indicating electron flow. Now they're asking which one is the cathode. Now, how are we going to decide on this one? We know that electron flow is always from the anode to the cathode. Now, given the arrow of the electrons here, we can see that these electrons are migrating from this half cell to this half cell here. So, or from this electrode to that electrode. So this means this has to be the anode and that has to be the cathode because the electron flow is always from the anode electrode to the cathode electrode. So that means we only have to say what? B. And then 8.3 says, write down the half reaction that takes place in half cell A. So in other words here, we must check our 4B table to see whether the barium or the copper is the anode. Remember, in half cell A, we have identified that now that is the anode. So we want to compare between the barium and the copper, which one is the anode and which one is the cathode. Okay, so this is how we're going to go about it. We're going to say we have barium. Do we have barium somewhere there? There's our barium. And then do we have copper? We know that copper is down here, right? So obviously from this one, we can tell the one that is above is barium. So that means our anode is the barium, right? So, okay. So they said, write down the half reaction. So we should write down the half reaction on that one. Remember, this is the oxidation now. right? So it's on the anode. So that means we have oxidation, but then oxidation is written from the right all the way to the left. So this is going to be what? This is going to be barium to give us barium ion plus 2E, right? So that's how you were supposed to write that. Awesome. Okay, so that's your 8.3 like that. Then they say now, write down the cell notation. Oh, you've been waiting for so long. So write down the cell notation for this cell. Now, how do we write the cell notation, guys? Since this is the anode, and then we have identified this is barium, we know that the barium, when it oxidizes and produces the barium ions. And then on this half cell here, we have the copper, which will reduce, the copper 2 plus ions will reduce to what? To copper, right? So note that when it comes to the cell notation, very important that you show even the phases. So we have our anode electrode here. So for 8.4, that's our barium. So this should tell you a story from the anode all the way to the cathode. So in the anode, we had this, which was in solid form. But then because that was the anode, it had to oxidize to barium 2 plus. But then this had to go through the what? The Sol bridge, right? And then from half cell A through the Sol bridge to half cell B. In half cell B, we find that on the electrolyte, we find the Cu2 plus ions. Okay, before we get there, these ones here are in aqueous. Remember, these barium ions will be produced from the will be produced in the electrolyte here, or will fall off in the electrolyte, which means they are in a solution, they are in a liquid there. So that's in aqueous solution, right? And then here, this is going to be in what? Cu2 plus, also from the electrolyte, so it's in aqueous solution. But then these ones, they reduce to form what? To form copper here. So we're going to have our copper and then in solid form, right? So that's basically how you indicate it. That was your barium in solid form that oxidized to barium ions. Then we went through the Sol bridge, and then in half cell B, we got the copper 2 plus ions, which reduced to copper. And then that's basically your cell notation, 4 marks for that. So always make sure that you are indicating the phases as well, right? So this here is what we call the phase separator. As you can see, when we draw a phase separator, usually your substances are in different phases here. So this is a solid phase separator aqueous, but this is just a Sol bridge, not a phase separator. So here, doesn't matter whether you have aqueous and aqueous here, but then as soon as you have a phase separator, then you must have a substance in another phase, right? So 8.5, they now say calculate the EMF of the cell. So we're going to have E cell is equals to E cathode minus E anode, right? So which one is on the cathode? It's the copper. So we already know that copper is 0.34, as we can see there. So we're going to have our 0.34 minus what? The barium is in brackets. Note that negative 2.90. So do not forget to put the thing in brackets, because we have a minus here, and then also we have a negative from the value there, so that we can end up having a positive value like that. So if you want to punch that into your calculator, that's 0.34 minus negative 2.90. So this is 3.24 volts, right? Then just like that, you have your value there. Okay, pretty interesting. Do we have another question after that one? Okay, let's see. 8.6 says, how will each of the following changes influence the value of the cell's EMF as calculated in question 8.5? Write down only increase, decrease, or remain the same. They say now, what will happen if the ammonium sulfate is added to the barium nitrate solution, right? So basically here, the barium nitrate solution, right, if ammonium sulfate is added to the barium nitrate solution, we normally say the barium nitrate solution is insoluble, right? So that means here in 8.6.1, actually adding the ammonium sulfate into the barium nitrate will not change the concentration, right? And if it doesn't change the concentration, that means the EMF will not be affected in any kind of way. So that means here, this remains the same. This remains the same. And then in 8.6.2, they say the temperature of the solution is increased. Now, this has to do with you understanding the nature of the cell that we have here, right? Now, this is what we refer to as a what? All galvanic cells, we normally say that what? They're exothermic reactions, right? Now, according to Le Chatelier's principle, we know that an increase in temperature favors an endothermic reaction, but it does a negative or it affects the exothermic reaction negatively. So the endothermic reaction, it would affect it positively, but then an exothermic reaction, it would affect it negatively. So because we are increasing the temperature here, and the nature of a galvanic cell is that it is exothermic, that means now what will happen? It means that the E cell now would have to decrease, right? Because now by increasing the temperature, you'd simply be favoring the reverse reaction, right? So you are not favoring the forward reaction, which is exothermic. You are now favoring the reverse reaction, which is endothermic. And in turn, it affects the E cell negatively. So that means now we have to say it does what? It decreases. It decreases. Right. Okay. So that's how you were supposed to go about answering this question for a total of 14 marks. Nice one. Let's look at another one. Okay, so now we have another question 8. It says in 8.1, a clean piece of copper Cu is placed in a solution of silver nitrate. The balanced net ionic equation is given below. Define oxidation in terms of electron transfer. So when they say define in terms of electron transfer, this is how you actually are supposed to define it. So you say oxidation is a loss of electrons, right? So from your oil rig. So remember, oxidation is loss of electrons, reduction is gain of electrons, right? Then 8.1.2 says, what type of reaction does copper Cu undergo in this equation? Choose oxidation or reduction. Explain the answer by referring to the oxidation numbers, right? So we already know this equation here, and then we know that the reaction that takes place there is oxidation. And then according to our oxidation numbers, we can even see here, Cu changes to Cu2 plus. So from 0 oxidation number to positive 2 oxidation number. Right. So that indicates what? An increase in oxidation number, which means that that is obviously what? Oxidation. If there's an increase in oxidation number, then it is obviously oxidation. Then 8.2 says sulfur dioxide gas SO2 is bubbled into an acidified solution of potassium permanganate as shown in the diagram below. Then that's what they do. It is observed that the solution turns from purple to colorless due to the reduction of MnO2 minus ions to Mn2 plus ions during the reaction. SO2 is oxidized to sulfate ions, SO2 minus 4. Determine the oxidation number of manganese in the permanganate ion. Now, from this here, Mn O42 minus. We understand that the 2 minus indicates the oxidation number of the whole permanganate ion, right? So, but then we know that the standard oxidation number of oxygen is what? -2, right? We don't know the oxidation number of manganese. That's what we are trying to find out. So we can represent the oxidation number of manganese as what? As X. And then we're just going to go about and say, now we have, using the MnO42 minus, we can say now we have X, but then we have how many oxygens? 4 of them. Each oxygen has an oxidation number of what? -2. Now, as a whole, the permanganate ion must give us an oxidation number of what? Of -2. So now what are we going to do? We are going to say X, 4 multiplied by -2, that's -8, is equals to -2. And then to calculate our X, we just simply need to transpose this -8. It becomes +8. And then X now becomes what? -2 plus 8. That's equal to +6, right? And that's how you would calculate that. So in conclusion, I will then say, therefore, Mn, or the oxidation number of Mn, is what? Is 6. So, okay, that's how we were supposed to solve this question for only 7 marks. Oh, yeah. Learners that year had it easy with this question. Imagine, just 7 marks. No calculation, no cell notation, no net cell reaction. Just answering those basic questions. All right, let's move to the next one. Okay, so we have another question 8. It says the voltaic cell represented below functions at standard conditions. Then they say, write down the concentration of the hydrogen ion in the one cell half reaction. Now, the hydrogen ion, we can see that it is part of the electrolyte there. So it forms part of the electrolyte. Therefore, it also has to have a what? A concentration of 1 mole per dm cube. So the concentration, we must just write 1 mole per dm cube, right? So it operates under what? Standard conditions. And then 8.2, solids present in half cells are usually used as electrodes. Give a reason why I2 is not suitable to be used as an electrode. Remember, for something to be used as an electrode, it has to be a metal that conducts electricity, right? So we just simply say iodine. We don't know iodine to have any properties of being a good conductor. So iodine is not a conductor. Even it's not a conductor, let's not even talk about it being a poor conductor or good conductor. It's not even a conductor at all. So iodine is not a conductor. Then 8.3, write down 2 properties of graphite. Remember, graphite, we say it's carbon in solid form, other than being a solid, that makes it suitable for use as an electrode in the above set. So again, it's more of what we mentioned. In order for something to be an electrode, it has to be what? A good conductor of electricity, right? It is a good conductor of electricity, number 1. And then also another thing that makes it okay for it to be used as an electrode is the fact that it will not tamper with the redox reaction that will be taking place here, mainly because it is what? Inert. It is unreactive, right? So the word inert means unreactive. So if it's unreactive like that, that means it will not be involved in the redox reaction that is taking place, but then will simply be there for the conduction of electrons from the anode to the cathode. That will be its only responsibility there. Okay, so yes, 8.4, for the above voltaic cell, remember, voltaic is another word for galvanic, right? So, ungatatazeli. Name of the oxidizing agent. Remember, the oxidizing agent will be found where reduction is taking place. So where reduction is taking place, that's the what? That's the cathode. Now, obviously, we must check here. Remember, what we are comparing is this and that. So, okay, now when it comes to identifying this, we have to identify the one that perfectly has all of this. The H plus, the MnO4 minus permanganate ion, and then also your Mn2 plus. We have to identify that one. So now let's go to our 4B table. So from our 4B table, let's look at, do we have iodine there? For iodine, there we go. So this is the anode. And then the other one there. So what are we being asked? What are they looking for? They're looking for the oxidizing agent. Oxidizing agent is on the cathode. So we still have to check. Now, do not be confused. As much as this one has the Mn2 plus, it has the H plus, it doesn't have the permanganate ion, right? So it does have everything else, H plus and Mn2 plus. But then remember, it does not have this MnO4 minus. So we must look for the one that has all of that. So this one, we're not going to take it. Now, let's look at something here. Here is our gold. Here is what we are looking for, right? MnO4 minus permanganate ion. We have the H plus, and then we have the Mn2 plus. Check, right? Now, obviously, when it comes to looking for the reducing agent, when we are looking for the reducing agent, we must always check where? On this side here, right? So the reducing agent is found on this side. So what would be the reducing agent? Okay, so we are looking for, let's check again. Keep on losing it. The oxidizing agent. Why I keep on saying the reducing agent? Oxidizing agent. Let's get it together. Oxidizing agent, you always have to look on the left. So oxidizing agent is right here. The one that undergoes what? Reduction. So remember, reduction, cathode, we are looking for the oxidizing agent. Therefore, we check this side, right? But then if it was here, this is the anode, and then that's where we have oxidation. We would be looking for the reducing agent. Okay, so now we are fine. So our oxidizing agent is the one on the far left. This is the oxidizing agent right here. Oxidizing agent. But then what did they say? Let's read the question. It said name of the oxidizing agent. Note that they don't want the formula, they want the name. So we said that thing is what? Permanganate ion. Permanganate ion. Right, there we go. Okay, nice. Okay, so there we go. Permanganate ion. Okay, then now we are on net cell reaction. So for the net cell reaction, we know what to do. So first, let's go with the half cell, the oxide half reaction, the oxidation half reaction. Then it's going to be what? So since we have identified from our 4B table that the oxidation is this one, right? So remember, we have to write it from the right going to the left. So this is going to be 2I minus to give us I2 plus 2E. And then we have our reduction half, which is going to be all of this exactly as it is. Exactly as it is, guys. MnO4 minus plus the 8H plus plus, okay, let me just mark it so that I don't lose it. There. 8 plus what? 5E to give us Mn2 plus 4H2O. Now, obviously, we want to balance the number of electrons, so we'd have to cross multiply. We see a 2 here, that means we're going to multiply everything by 2. We see a 5 here, that means here we're going to multiply everything by 5. Now, if we multiply everything by 5 here, then we end up with what? We end up with 5 times 2, that's 10, I minus, to give us what? 5 multiplied by this, that's 5 I2, and then 5 multiplied by that, that's 10 E minus. right? So that becomes our oxide half. Now for the reduction half, remember we have to multiply everything by 2. So that's your 2 MnO4 minus plus 16H plus 10E, right? And then to give us what? 2 Mn2 plus, and then plus 8H2O. Now let's cancel out the electrons because that's the whole purpose of us doing this, right? We want to eventually cancel out the number of electrons, right? So this cancels out with that, but everything else will be written as it is there. So we're now going to have what? 10I minus plus the 2MnO4 minus plus the 16H plus. So that's everything on the left. Now let's write everything on the right. That's 5I2 plus 2Mn2 plus 8H2O. Right. And that's our net cell reaction. So yes, this was pretty interesting. Pretty interesting. Right. Nice one. So make sure that you pay attention on that one. Pay attention on that one. Okay. Then what's the next question? Whoa. So now we are asked to write the cell notation. Cell notation, guys. Okay, so for the cell notation, note that here we had to borrow a what? We had to borrow the anode and the cathode and use graphite, mainly because on this side here, we couldn't use this iodine since we said it's not a conductor. And also when we check here, there is nothing that was in solid form, right? So there's nothing from these ones that we had here that would stand here as a what? As an electrode, right? So hence we had to employ the graphite in both the anode and the cathode electrode. So now when we write the cell notation, we are supposed to indicate that. Remember, the cell notation is not like the cell reaction. The cell notation, we have to indicate our anode, our cathode. So, okay, we have identified that this is the anode, right? So this will start from here. We want to start with our carbon, which should be in solid, and then phase separator. Now, this will be followed by what? Remember, when we come to this, we said our reaction is 2I minus to give us what? I2 plus 2E. So in other words, we are saying that the iodine ion will reduce to what? This iodine ion will oxidize, right? Will oxidize, not reduce, will oxidize to this. Because remember, this is from -1 to 0. This iodine atom here has what? 0, right? So this has 0 oxidation up. This has -1 as an ion. So from -1 to 0, that's an increase in oxidation number, meaning this is oxidation, right? So remember, even when you write it here from the cell notation, it should indicate that oxidation took place. So if oxidation took place, that means we have to start from the ion here, which is I minus, right? Which is in what? Aqueous solution. But this I minus actually oxidizes to I2 solid, right? So this is the one that oxidizes to that. Should be careful of that. And then from here, we have our salt bridge. Then what is it that we meet with here? We can say we have our H plus. So this is, okay, so I should have wrote it a little bit further. So solid, and then I minus in aqueous, and then we have the I2 solid, and then we have the salt bridge, followed by our H plus in aqueous. Now remember, because everything in here is in the same phase, there would be no need for us to include phase separators. Remember, phase separators are only used to separate different phases. But then if everything here is within the same phase, then that means we only want to have semicolons to separate that. So we have MnO4 minus, and then it's in aqueous. And then also we have our Mn2 plus, which is in aqueous, right? But then remember, we must close it off with a what? We must close it off with a phase separator, and then we close it off with the cathode. Now, our cathode is also graphite, which is your carbon in solid form. And therefore, your net cell your cell notation will look like this. So that's your cell notation. So it was very, very important or crucial for you to actually note this, right? The fact that the iodine ion oxidizes to iodine atom here. The iodine ion oxidizes to iodine atom. So hence you had to indicate it like that. And then also make sure that you are showing all the phases there. And then, yeah, that's your cell notation. So this one was pretty interesting. So you can come back to this one and practice it. Okay, so we have 8.5. It says now calculate the cell potential. So we have E cell is equals to E cathode minus what? E anode, right? So the cathode, we've already identified it to be the one with the permanganate ion. So we're just going to go, where is it? The one with the permanganate ion. That's positive 1.51. And then minus, we have identified the one with iodine is 0.54, right? Then when we subtract the 2 there, this gives us 0.97 volts. So that's your E cell, right? So just like that, you have your 4 marks. Then, nice. How will the reading on the voltmeter be affected if the concentration of the permanganate ion decreases, right? Only increase, decrease, or no effect. Note that the permanganate ion is on the cathode, right? What is the relationship between E cell and E cathode? So for 8.6, E cell is directly proportional to E cathode. So that means if we increase the concentration on the cathode, the E cell will also increase. But what happens if we decrease? If we decrease the concentration on the cathode, then even E cell must decrease. So which is what they told us here. The concentration of MnO4 minus decreases. So that means what will happen to the E cell? It also has to decrease. So it decreases, right? Okay, so that's it, guys. That's it. So all of this for 16 marks. Right. Let's see another question. All right, we have another question. 88 says, a learner wants to investigate the effect of the area of the metal plates used as electrodes in a galvanic cell on the EMF of the cell. The learner sets up the following cell under standard conditions and measures the EMF. 8.1 says, which electrode will show an increase in mass when this cell is functioning, right? Okay, so we do know that the one that shows an increase in mass has to be the cathode electrode. So it's just a matter of checking between the PB, lead, and zinc, which one is actually the cathode, right? So we know that our anode is above and then our cathode is below. So let's check. We can see that the first one that we see is zinc. Then where is PB? PB somewhere there. Right, there we go. So that means this would be the anode, which the anode, we know that there will be a mass decrease, but then this is the cathode where we'll observe a what? A mass increase, right? So the mass increase happens in the cathode because remember, in the cathode, that's where we have reduction. Reduction is gain of electrons. Where there is a gain of electrons, there will be a mass increase, right? Okay, so that means our solution for that one is going to be for 8.1. We are going to say PB, right? Okay, then we have 8.2. It says write down the equation for the half reaction occurring at the anode, right? Now that we have identified that this is the cathode, then that means zinc here is the anode, right? And then how do we write the half reaction for the anode? We already know at this point that we should do what here? This is the point whereby we should take the zinc here, but then we write it from right to left because that's oxidation, right? So we're going to indicate this is zinc to yield as zinc 2 plus 2E, right? And that is our thing right there. Okay, then let's move. We have 8.3. It says calculate the EMF that the learner will read on the voltmeter. Again, here we go E cell is equals to E cathode minus E anode, right? Now, what is our cathode? Our cathode is the PB, right? Then where is PB? PB is this one with the value of negative 0.13. And then the anode is the zinc right here with a reading of negative 0.76, right? Now, punching all of that into your calculator, you get 0.63 volts, right? Then for 4 marks, that's all you are supposed to do. Nice one, right? Then what's the next question? Wait. Then it says name 2 variables that should be controlled during this investigation. So this is a cell that operates under standard conditions. So we know that what should be kept constant is the concentration of the electrolytes, right? Concentration of the electrolytes, right? So they must always be kept at what? At 1 mole per dm cube. Right, so concentration of the electrolyte should be 1 mole per dm cube. And then also what else? It must be the temperature, right? So this must be the temperature, which we know it must always be kept at 25 degrees Celsius. So you just mentioned that it's the concentration of the electrolyte and the temperature. Now, do not mention pressure once again, because we do not see any gases there, right? So note that. Okay, then let's move. They say now in 8.5, the learner now replaces the 2 metal plates with one of larger surface area and takes the voltmeter reading again. How would you expect the new EMF to compare with the one calculated in question 8.3? Only write smaller than, larger than, or equal to. Now, we don't really know the surface area having an impact on the voltmeter reading. We haven't read it anywhere else, and then we do know that the surface area has no relationship with the voltmeter reading. So we're just gonna go with equal to, right? Equal to. Then 8.5.1 meant to say. Then 8.5.2, we're just simply gonna say the area or the size of the electrodes has no effect on the EMF. No effect on the EMF. What we know to have an effect on the EMF would be the concentration of the electrolytes, right? If we increase or decrease the concentration of the electrolyte, depending on whether we do it on the cathode or the anode, then that does impact the EMF, or does have an effect on the EMF. But then as for the area, the size of the electrodes, where we do not know that to have any effect on the EMF. So that's how we go about it, right? Then for 8.6, it says the learner now connects a resistor of low resistance across terminal A and B, right? The learner notes that the reading on the voltmeter immediately drops. Give a reason for this observation. Now, you know from electric circuits, right? The fact that if we connect that, it means that the cell on its own has what? So give a reason for this. It might be that the cell has internal resistance. So from grade 12 electric circuits, we know that any battery or cell has internal resistance, and then the battery doesn't normally give off all of its EMF, right? Then from the EMF, we know that your EMF breaks down to the V external and also the V internal. And then only the V external gets to flow throughout the external circuit. So we're going to say the cell has what? Internal resistance. So this is the same analogy that says if you have an EMF, maybe a battery that has an EMF of 12 volts, then you can find that the voltage that gets supplied into the external circuit is only 10 volts. And then let's say maybe 2 volts remain as the internal voltage because it is taken by the internal resistance of the battery, right? So more on that when it comes to electric circuits. And then after some time, the learner observes a further gradual drop in the reading on the voltmeter. Give a reason for this observation. Now, why is that? So we want to respond to that based on what happens on the cathode, right? So it might be the fact that the concentration of the Pb2 plus ions are being reduced here. Remember, as this is taking place here, the Pb2 plus ions are being reduced to the Pb. And that means the concentration of the Pb2 plus ions here are actually decreasing. And if this concentration decreases, that means that the E cathode actually goes down. And then actually, because of the E cell being directly proportional to the E cathode, it means if there is a drop in the E cathode, there is a drop in the E cell, right? So 8.6.2, we are just going to go with this. The EMF decreases. The EMF decreases as a result of the concentration of the Pb2 plus ions decreasing. Right, so the EMF decreases as a result of the concentration of the Pb2 plus decreasing. Right, so when there is a decrease on the cathode there is a decrease also in the E cell. Right, remember as that reduction is taking place. Okay, so that's how you were supposed to go about answering all of this question for a total of 14 marks. So right, easy peasy right there. Let's move to the next question. Okay, so we have yet another question 8. It says a standard electrochemical cell is set up as shown below. Then 8.1 says state the energy conversion that takes place. Now we know with a galvanic cell, it is always what? A chemical to electrical energy. Chemical to electrical energy. Then, okay, now in 8.2, they say component Y ensures that the cell is complete. State one other function of component Y. So component Y is a cell bridge. And then another function is that it provides a path for the movement of ions. For the movement of ions. Or you can mention that it ensures electrical neutrality. Ensures electrical neutrality in the cell. Right. So that's how you go about it. You can mention either one of those functions there, and then you'd get your full marks, right? So they only need one, remember? So you can just say provides a path for the movement of ions, or you can say ensures electrical neutrality in the cell. So they've already given you the function that it completes the circuit. Then 8.3 says calculate the initial EMF of the cell. So how do we go about it? We're going to say E cell is equals to E cathode minus E anode, right? And then from here, we have to identify which one is our cathode, which one is our anode, right? But then we simply want to be checking that based on what? Based on the Pb2 plus and also the what? The Fe2 plus and Fe3 plus. So remember, we cannot include this because what do we see here? This is platinum. And then platinum is not part of this because platinum is what? Is inert. So the platinum here is only acting as an electrode. It does not take part in the redox reaction. We say it is what? It is not active. Not active. So it's not active in the redox reaction. Therefore, it does not form part of any of the reduction reaction or the oxidation reaction. right? It is only there to act as an electrode, just to facilitate the movement of what? Of ions, right? Or to facilitate the movement of electrons from the anode to the cathode, right? And then, okay, now 8.3, let's look at our 4B table now, so that we can correctly identify the ones that we need to. So remember, this is about looking at what you need to identify exactly, right? So we have the PB. So where's PB? PB, that's it right here. But then the ion that we should take is not this one. So we can see we have Fe2 plus, but then this side is Fe. Remember, we must look for the one that has Fe3 plus and Fe2 plus exactly as it is, right? So we can't go with this one. This one would be incorrect, right? And then, okay, we keep on searching and then we see this one. Would this one be correct? No. As much as we have the Fe3 plus, we don't have the Fe2 plus. Remember, we must pick the one that is exactly the same. Now, let's look at something here. We have magic here, and then this one, exactly the same at positive 0.77. So let's check. That's exactly the same with this one, Fe2 plus and Fe3 plus. Okay, so that means we're going to take that one. And then now, this is our E cell now. So this has to be the cathode, and this has to be the anode. So cathode, positive 0.77 minus negative 0.13, right? And then when you punch all of that into your calculator, you get what? 0.90 volts. Right, so that's how you were supposed to go about answering that one there. Hey, nice. And then now the next question is saying what? The next question is saying, okay, so the next question is saying, how will the reading on the voltmeter be affected if, okay, so, okay, oh, wait, I answered 8.4. This is 8.4. So I skipped 8.3. So let me go to 8.3. Write down the reduction half reaction. So since we mentioned that this is, which one is the cathode? This one, right? So we mentioned that this is the cathode. Then this is the equation that we should be having there at 0.77, right? So it is a reduction, so it must be written exactly as it is. Fe3 plus E to give us Fe2 plus, right? So pardon me there. This is supposed to be 8.3 and that is 8.4. Okay, then now they say, how will the reading on the voltmeter be affected if choose from increase, decrease, or remain the same? If the initial concentration of the Pb2 plus is increased. Now this is on the anode and this is the cathode. Now we are increasing the concentration on the what? On the anode. What happens if we want to increase the concentration on the anode? So initial concentration of Pb2 plus increases. So if we want to increase the concentration here, that means what happens is that for initial concentration, what happens is that that one has to what? Has to increase, right? So it increases. And then the surface area of the PT electrode is increased. So if we increase the surface area, we know, we have answered it in the previous question, that the surface area has no effect on the EMF, right? So we're just going to say remains the same. Remains the same. And then now they say the Pb2 plus half cell is replaced with zinc 2 plus, right? So what will happen if we want to be replacing it with that? Let's see. So it's just a matter of reading of the distance now. So let's see. So initially we are having the Pb, right? So that's the Pb, and then to what? To this Fe3 plus E. So look at the distance in between initially, and then let's look at the other one now. So we are replacing it to this. We are replacing it to this one. Now, obviously, when we replace it to that, the distance from here all the way from the anode to the cathode becomes bigger, right? So indicating that even the E cell now will become bigger. So E cell increases. So we just have to say increases. Okay, there we go. Then let's check now. 8.6 says explain the answer to question 8.5.3 by referring to the relative strengths of the reducing agents. Okay. Let's explain that. So we're going to say, again, if we do what we did, so this is the zinc. Where is it? This is the zinc right here. And then this was the Pb2 plus. Right. So now looking at this, when we are comparing the two here, when we are comparing the two, we can see that zinc here is a stronger what? So we can say zinc is a stronger reducing agent than Pb. So that means the reaction between zinc and this one here, and Fe 3 plus will be more strongly favored. As it releases more energy. Per unit charge. Right. So zinc is a stronger reducing agent than Pb. The reaction between zinc and Fe3 plus will be more strongly favored as it releases more energy per unit charge. Right. In comparison to the one for Pb all the way to here. So we can see that based on the distance and based on the E cell. Right. So much more energy is released here than it is when it comes to this. Okay, so nice. So that was a very nice question there. For 2 marks, that's all you were supposed to state there. So nice, 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 nice. Okay, so we have this question 8 here. It says dilute hydrochloric acid HCl reacts with magnesium and then at 25 degrees Celsius, so which is your standard temperature, according to the following balanced equation. They say use oxidation numbers for each of the reactants and explain why this reaction is a redox reaction. So what we want to start with is just laying down all the reactants that we have here. We have magnesium, which is an atom, so it means that it has an oxidation number of 0. And then this one obviously has to ionize. When it ionizes, it breaks down to H plus and then Cl minus, right? So we know the ionization of hydrochloric acid. And then so that means we have our hydrogen ion, which has an oxidation number of +1. We have our chlorine ion, which has an oxidation number of -1. So these are the reactants. Okay, so we're just going to separate them from the product. And then we say if we look at the same substances on the product side, here if we want to ionize the magnesium chloride, then it ionizes to Mg2 plus and then Cl minus. So we want to have our Mg and then 2 plus. And then right here, we still want to have Cl minus. And then what happens to the hydrogen? The hydrogen just becomes a molecule, so meaning that it now has an oxidation number of 0. So here oxidation number changes to 0. Here oxidation number changes to +2. Here oxidation number still is -1. So what do we refer to chlorine as? So we're just going to say that chlorine ion has to be what we call a spectator ion. Now remember, what is a spectator ion? It is an ion that does not change its oxidation number from the reactant side to the product side, from the beginning of the reaction to the end of the reaction. So this one, let's just say spectator ion, right? Spectator ion. So that means here, in order to prove that a redox reaction took place, we just have to reason based on the magnesium and the hydrogen, because we can see that those ones did actually change their oxidation number. So if there's a change in oxidation number, it means a redox reaction occurred, right? So we're going to say from magnesium O to magnesium 2+, there is an increase in oxidation number. There is an increase in oxidation number, indicating an oxidation reaction. And then when it comes to the H+, we're going to say from H+ to what? To H2, which has an oxidation number of 0. Here, there is a decrease in oxidation number, indicating a reduction reaction. Right. So as we can see now, that means a redox reaction did take place, because we see oxidation here and then we see reduction there. Then 8.1.2 now is saying, write down the formula of the oxidizing agent. Remember, the oxidizing agent is the one that undergoes what? Reduction. So which substance underwent reduction here? It is the H+ ion, because it moved from +1 all the way to what? All the way to 0, right? So that means it's a reduction, a decrease in oxidation number. So we're just going to go with H+. Okay, so let's now see. So 3 marks already. It is observed that dilute hydrochloric acid does not react with copper at 25 degrees Celsius. Explain this observation by referring to the relative strengths of the reducing agents. Okay, so let's see this. So this is between copper and the hydrogen, because remember the chlorine, we said it's a spectator ion, so it will not really contribute to anything in this redox reaction. So that means here we are looking for copper at 0.34, and then we are also looking for hydrogen, right? They said refer to the relative strengths of the reducing agents. So we can see that the strength of the reducing agent is increasing from the bottom all the way to the top, meaning this is weak and this is strong, right? Strong reducing agent, weak reducing agent. So we're going to say copper. Remember, when we are talking about reducing agents, we are talking about these ones on the right here. So copper is a weaker weaker reducing agent. So it's a weaker reducing agent than hydrogen gas. So meaning copper will not reduce the H+ ion to hydrogen gas, because it is a far weaker reducing agent. Remember, a reducing agent is responsible for making this other substance to reduce, while in turn it will do what? It will oxidize. So copper is a weaker reducing agent than hydrogen gas. That means copper will not be able to make what? To make this H+ ion to reduce to what? To hydrogen gas. Okay. then that's how you explain that. So that's how you explain that. So that question was for 8.1.3. Let's indicate 8.1.3. Okay, now they say, will dilute nitric acid HNO3 react with copper at 25 degrees Celsius? Choose yes or no, and then explain the answer in terms of the relative strengths of the oxidizing agents this time. So if they're talking about oxidizing agents, where are we checking now? We are checking on this side. But then this one, when it ionizes to what? It ionizes to H plus and then NO3 minus, right? What we are mainly focused on right now is the NO3 minus, right? And not necessarily the hydrogen. So, okay, let's check which one has NO3 minus. So you will also observe that NO3 minus also includes the H plus, which means that everything has now been included. So we want to go with this one. We want to go with this one. And then in comparison to what? In comparison to, so they say, will it react with what? Okay. Will it react with copper? Will it react with copper? Remember, the copper that we want is the one in 0.34, positive 0.34. Now we can see that the strength of the oxidizing agent is increasing as you go down, right? It's increasing as you go down. So we want to say, yes, NO3 minus. So our answer will be yes, NO3 minus. Remember, when we are talking about oxidizing agents, we are referring to the ones on the far left. NO3 minus is a stronger oxidizing agent than Cu2 plus, right? Which means, therefore, the copper will be oxidized to copper 2 plus. So since this is a stronger oxidizing agent, it will be able to make that copper to reduce to what? To Cu2 plus. It will be able to make that Cu to be, it will be able to make that Cu to be oxidized. This is a stronger oxidizing agent, so that means it will be able to make the copper to be oxidized to copper 2 plus. Makes sense? So yes. So that's how you get that. So a mark for saying yes and a mark for having to explain this. So NO3 minus is a stronger oxidizing agent than Cu2 plus. Therefore, it will be able to make the copper to be oxidized to copper 2 plus ion. Okay, then we move now. It says a galvanic cell is represented by the following cell notation. Write down the balanced net ionic equation for this cell. As mentioned on the previous question, we said the platinum here is just an inert substance, right? Only acting as a what? As an electrode, but then it is not active. Not active, it is not involved in the chemical reaction. So when we write the balanced net ionic equation, it will simply be for the Pb and the ion there, right? So obviously from here, let's check. Already from the cell notation, we can see that this is the anode and this here is the cathode. So to write down our balanced equation, let's start with our oxidation half reaction. So this will just go as what? Pb to give us what? Pb 2 plus 2e. And then our red half, it's very simple to write this from here. This is just going to be Fe 3 plus E to give us what? Fe2 plus. If you are not sure, you can still check your 4b table, right? Where you will identify the two reactions. So we have the reaction for Pb2 plus. There we go. Which because it is oxidation, it must start from this side and then go that side, from the right to the left. And then we also have the other one at 0.77, exactly the same. So that's the one. And then you are supposed to write it exactly like that. Then for your net cell, we can see that your number of electrons are not balancing. So that means multiply, cross multiply. We see a 1 here. So we're going to multiply by 1. We see a 2 here. We're going to multiply by 2 down here. So which means 2 multiplied by this is 2Fe2 plus. And then we're going to have 2 everywhere here. But then if you multiply everything by 1 here, it still remains the same. So which means at this point, we can cancel out this and that. And then it's just a matter of dropping everything on the left, Pb plus 2Fe3 plus. And then this will give us what? Pb2 plus 2Fe2 plus, right? And then that's basically what we have right there. Awesome. So we now have our net cell reaction. So note that the platinum is not involved here. Okay, then a stronger reducing agent is now used with the same oxidizing agent under the same conditions. How will this affect the initial EMF of the cell? Choose from increases, decreases, or no effect, right? So now that means they're using a what? A stronger reducing agent. If they're using a stronger reducing agent, note where do we find a stronger reducing agent? A stronger reducing agent would have to be found above, right? So that means we are taking it further above. It could be anything that is above the Pb2 plus. So if we are taking something that is above, that means the distance now becomes longer. So that means it would have to be this, where is it? This Fe3 plus. And then let's say they choose to go with zinc instead of the Pb. So instead of this, they choose to go with zinc. Now, obviously, considering now the distance from the anode to the cathode, we can now see that obviously the E cell will increase, right? So that in comparison to this. So what will happen to the E cell? It has to increase. So for your 8.2.2, you're going to say increases. It increases, right? So yeah, that's basically how you were supposed to go through that question there. Awesome. Let's see another one. All right, so we have the question 88 says the following balanced chemical equation represents a redox reaction taking place when a galvanic cell is in operation under standard conditions. The initial reading on the voltmeter is 0.14 volt. Write down the two standard conditions under which it operates. So for 8.1, we are going to say temperature of 25 degrees Celsius. And then we have what? Concentration of 1 mole per dm cube for the electrolytes. And then since we can see we have chlorine gas here, we can even mention, though we already have 2, but then you can also mention pressure of 101.3 kilopascals, right? So they only want 2, right? So that means if you can mention any of the 2 there, it would be correct. Remember, you only mention pressure if there is a gas. Now for this cell, write down the name or formula of the electrolyte that can be used in the Saw bridge, right? So what can be used? Most of the time they use KNO3. So they said name or formula. KNO3 is potassium nitrate, right? So whether you use you write the formula or the name, then you'd be correct. Potassium nitrate. And then 8.2.2, give the name of the reducing agent. Now the reducing agent is the one that undergoes what? Oxidation. So we are looking for where we will see a what? An increase in oxidation number. Which one indicates an increase in oxidation number? If we can look at this one, this is from an oxidation number of -1. This is oxidation number is +3. This side here, oxidation number, because now it is a molecule, it's 0. And then oxidation number here also, this one is what? Is, okay, so 3 plus and then 2, 0. Which one is showing an increase in oxidation number? So increase in oxidation number would have to be this, from -1 to 0. So it's becoming what? More positive or less negative, right? So if you look at the numbers from -1 to 0, we are moving to the right side of the number line. So that indicates what? Oxidation. But then from +3 all the way to 0, we are moving to the left-hand side of the number line, which indicates what? Reduction. So reduction if the number becomes smaller, oxidation if the number becomes bigger, right? So that means the one that is a reducing agent here has to be what? Cl minus, right? The chlorine ion. Okay, then 8.2.3, the cell notation now. Okay, so for cell notation, we have to say now, we have our, so since here we can see that on the anode, remember, this represents the anode. But then remember the Cl minus or the Cl2 cannot be an electrode, right? Because simply this is in aqueous state and this is in gaseous state. Remember, for the electrode, we need something that is a metal and then it's in solid form, right? So this is where we get to put the platinum as the electrode, right? So that means when writing our cell notation, we want to start with platinum, which is a solid. And then now we have the Cl minus in aqueous, which is now supposed to do what? Oxidize to give us what? The chlorine gas. Okay, let me just write it here. 8.2.3. We start with our platinum in solid. And then we have now the Cl minus, which does what? Oxidizes to Cl2 gas and then goes through the what? Soil bridge. And then here we have the Au3 plus in aqueous, and then we have what? Au solid, right? So take note of this. Since this two here, none of the two can act as an electrode, we have to employ the platinum electrode there. And then, okay, calculate the standard reduction potential of Au, right? So this is how we're going to calculate that. So note that we are already given the what? The E cell. So we're just going to go E cell is equals to E cathode minus E anode. Now we have 0.14 and then we don't have this one, E cathode. So that is going to be minus the E anode. Now the chlorine, let's check it up. What is the potential? The cell potential for the chlorine? Cl. Where is it? Okay, there is it. 1.36. 1.36, and then we're going to take it over to the side. So that will become E cathode is equals to 0.14 plus 1.36. And then when we do our calculation there, it's going to be 1.5. So that's your E cathode. Now, can we confirm? Do we have it there? Do we have Au somewhere here? $1.5. Not quite. So that means we were calculating something that does not appear here. Okay, so Au is what? Au is gold. So yeah, it wouldn't appear here. Okay, nice one. So that's how you were supposed to go about calculating that one right there. Awesome. Next question. Okay, so we have this question 8. It says the diagram below represents a galvanic cell functioning under standard conditions with magnesium and iron as electrodes. The net cell equation for this cell is as follows. Then in 8.1, they say, for this cell, write down the energy conversion that takes place. Now, already we know at this point, it is a chemical to electrical energy. And then 8.1.2, they say two standard conditions. Now, again, temperature of 25 degrees Celsius, and then concentration of 1 mole per dm cube. And then 8.1.3, the electrode which acts as the cathode, and give a reason for the answer. So from here, we just have to compare the magnesium and the iron. So note that the one that we are looking for is exactly the one that goes Fe and Fe3+. It's very important, guys, to note that. Then we have the magnesium. Where is magnesium? There is it. And then let's check for the one that is like that. Fe, where are you? Not this one. So we're not going to take this one. As much as it has the Fe3+, but then we want Fe on this side. There we go. Nice. Fe3+ and Fe as an atom here. Right. So it must actually gain 3 electrons. So this one is the cathode. This one is the cathode. So we're going to say it's the Fe. Right? Fe. Why? Because reduction takes place there. Reduction takes place at this electrode. Right. Okay. Now, they say write down the reduction half reaction. Okay, wait. Sorry. Okay, 8.1.4, the oxidation half reaction. Oxidation. So since we said this is the cathode, then this here is the anode. And then as we know, when it comes to oxidation, when we check here, we know that from this magnesium, we have to start it from here, going in that direction. So it's going to be the Mg. I keep on viewing the wrong one. It's going to be the Mg to give us what? Mg2 plus 2E. Okay. Then the cell notation, 8.1.5. So as we can see, all of this here can stand in their own place. So we do not need to have any inert substance there. We have our electrodes and then their active electrodes. So this is magnesium, which is in solid form. It oxidizes to magnesium 2+, which is in aqueous form, and then goes through the salt bridge. Here we find the Fe3+. So note that we are indicating the cell notation, not the net cell reaction. In aqueous, and then this reduces to Fe, which is in solid form, right? And just like that, the name of the component responsible for electrical neutrality of the half cells. Duh, we already know, salt bridge. Right, then calculate the initial EMF of the cell. So how are we going to calculate that E cell? is equals to E cathode minus E anode. And then what's your cathode? So this is the anode. And then a cathode, we identify it here. So this is going to be what? Negative 0.06 minus negative 2.36. And then when you punch all of that into your calculator, that gives you 2.3 volts. So that's your E cell right there, 4 marks. Okay, so that's how you are supposed to tackle all of this question here for a total of what? For a total of 15 marks, right? So nice one. Nice question right there. So guys, that's about it for all of these questions, guys. So make sure that you practice as many questions as possible, and then make sure that you just go through everything that you have to know right there. So I've tried to show you all those cells, most of the questions there that are exam type questions from your past exam papers. So make sure that you go through this video, share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.